Hey guys, I'm Kevin, and today I'd like to share with you some of my favorite experiments, and they have to do with polarization. So what exactly is polarization? Well, light is an electromagnetic wave, and so it has an electric component that oscillates, that goes up, comes back down, and keeps doing that as it moves through time, and also as it moves through space. But it's electromagnetic, so it's got this electric component, but it also has a magnetic component. And this does the same thing. It oscillates up and down and back. Now, they go together, and so we have they go together in a very particular way. In fact, the magnetic component is exactly perpendicular at right angles to the electric component. So it looks something like this as it's going through space. So you can see the magnetic and electric fields oscillate together and they're out of phase. So this light is linearly polarized because the electric field just goes in one direction. It goes straight up and down. Now, if we're say like this, that's going to be vertical polarization. And we move it this way, we call that horizontal polarization. Now, light doesn't have to be just vertically polarized or just horizontally polarized. It can be anywhere in between. Light sources that produce light that's polarized all over the place is what we call unpolarized light. So this is a flashlight, and it's going to produce unpolarized light. And I can demonstrate this for you by using a polarizer. So this polarizer here is labeled axes, and it has a little arrow, and that shows you which way it lets through, or which polarization it lets through it. So the first thing you notice is that this is somewhat dimmer than the background, and that's because it's not letting all the light through it. It's only letting the light that's polarized, in this case, with the electric field horizontal. So if we look at our light source through this, it's dimmer, but it's still there. Now we can rotate it around, and again, light's still getting through. So we have light that's getting through that's both vertically polarized, horizontally polarized, and everywhere in between. Now, if we expand this and we take another polarizer, it's just the same. Again, now we've got the axis horizontal. We can have light pass through one polarizer and the other one. So if we put them this way, you see all of the light gets through. And that's because after it goes through this one, it's horizontally polarized, and that horizontally polarized light makes it through the second one. Now, if we rotate these so that one of them is perpendicular to the other one, now all of a sudden, no light's getting through. And that's because the light that comes through this one first, to show you how these are set up like that, is all horizontally polarized, but this one only lets through vertically polarized light. So as a result, no light gets through. Do this with our flashlight again. Okay. Now, I said we were going to use polarized sunglasses. So first of all, let's find out how they're polarized. We can use one of our polarizers that we know which way it's polarized, and put it here in front of the light. That's producing horizontally polarized light. And we can start with our sunglasses, start rotating them around. So you can see the light makes it through. There it gets pretty dim. Starts getting brighter again. I think that's maybe the brightest. And then back around. So it's dimmest right about here. So which way does that mean that the sunglasses are going to have to be polarized? That's right, vertically. So we can go ahead and mark our sunglasses as vertical polarizers here. And now, let's do something interesting. So we have our sunglasses. We have our initial polarizer here. This is horizontally polarized. Sunglasses are vertically polarized, more or less. There we go. I think that's the best I can do. What happens if I use another polarizer, but I stick it in instead of, well, if I stick it in horizontally, it's about the same. If I stick it in vertically, well, it eliminates that light there. What happens if I stick it in an angle? Let's find out. Oh, actually gets brighter. That's interesting. What's going on there? So that was kind of interesting. What's going on there? Well, let's take a look at it step by step. So we have our flashlight first, which produces unpolarized light. So we've got some vertical, some horizontal, side to side. And then we pass it through a polarizer, which only lets through horizontally polarized light. Then if we had what we call the analyzer, the sunglasses, just vertically polarized, that would block all the light. But we don't. We have this other polarizer set at an angle. So when this light arrives at the polarizer, it's horizontally polarized. I'll draw that as a black line here. But then the polarizer is at an angle, like this. So that's going to let through light that's at this angle as well. And so some of this light that arrives at it is going to get repolarized along this diagonal. Now similarly, we come to our analyzer, pair of sunglasses here. They're polarized this way. The light that arrives is diagonal. And again, there's some component of that that is now vertical, and that makes it through to our eyes. So that's now why we see an increase from what was previously zero light there. Well, that's kind of neat, but you could be asking yourself, is there an application for this? And there sure is. It's in liquid crystal displays. So the way a liquid crystal display works is it has a back pane that's illuminated from the source behind it. And this pane is polarized again, and it has a front pane on it that's cross-polarized. So normally, no light gets through. However, what they do then is they put in some liquid crystal. What that liquid crystal is this kind of rod-like material, and it aligns itself naturally here with the polarization axis, and then it rotates slowly up to this front analyzer axis. And so in that case, what we actually have is, as it's rotating the light with it. So it's as if we were having this angled polarizer in there, and we're getting some light through. When we apply a voltage, though, the rods, they all shift, and so they go flat, and it's as if we removed it and we get something dark. So where do we use LCD screens? Pretty much everywhere. We have them on our calculators and of course also on our computers. So here I pulled up just a blank PowerPoint slide, and I'm going to show you that the light coming out of the monitor is polarized because it has that final analyzer on it. So we've got our polarizer here, put on our polarized sunglasses, and we can rotate them down, and you can see that indeed we block out most of the light, and it comes back. So the light coming out is polarized, and that's actually pretty well polarized too. So we'll leave them on, and let's do something cool with this. Actually, I'm going to take this off for a minute to show you. We're going to look at the stress in this petri dish. So if we just look at the petri dish, then, yeah, I mean, it looks okay. We can kind of maybe see something at an angle. So if we put on our analyzer, and then look at the petri dish, whoa! Now we get a bunch of bright colors. So what's going on there? Any ideas? As the light is passing through the petri dish, it's getting rotated just as it was passing through the rotating liquid crystal, and that lets more and less light through. And since the petri dish is very uneven, some areas of it pass through, for example, more red than blue, and that gives us this nice rainbow effect. It's also very striking, of course, if we rotate the analyzer, so we're not seeing a whole lot of light, and then we put it in there too. Now, if you're wearing your polarized sunglasses, you're probably outside. And one of the things you might notice is that the sky changes its darkness as you change your head. So right now I've got the camera without any polarizers on it, and let's take a look at this. So here's our polarizer with the axis labeled. Again, it's pointing this way. So let's move this around, and then if we rotate it, notice that it gets brighter, so it's letting more light through this way, and then darker if I rotate it this way. So in fact, the light coming from this part of the sky is vertically polarized. Now, is that the same for all parts of the sky? Not entirely. That one's actually doing pretty good over there, but over here it's about the same. Now, why is that? So the sun is over there. The sun's emitting light towards us, and that light is unpolarized. But then when it scatters off the atmosphere here, it has to scatter and then come back down towards us this way. So the light's coming in this way, it excites the molecules like this or like this, and they're vibrating. When they re-emit that light, it's all polarized this way. Hence why the polarizer lets light through when it's vertical and blocks it when it's horizontal. And then if we go this way, which is about opposite the sun, there the effect is diminished, and that's because the light waves coming in unpolarized, exciting the atoms in the air, and they're re-emitting unpolarized light back at us. So that's the sky as seen under polarization. Some interesting facts are that bees will use this to navigate by. So light doesn't have to be just vertically polarized or horizontally polarized. That's what we call linear polarization. It can also be what's called circularly polarized. So what that is we had our electric field and we had our magnetic field. So let's just take a look at the electric field for a minute. In linear polarization, the electric field is going straight up and down, linearly in a line. In circular polarization, as that electric field moves through space, it's also rotating. So at one point in time it's vertically polarized, and at another point in time it's horizontally polarized. And just like we can have vertical and horizontal polarization, we can have right circularly polarized or left circularly polarized depending on how this field rotates as it moves through space. Now, the question is, have you seen circular polarizers? Well, I bet you have. For example, if you've been to a 3D movie. These are real 3D glasses, and how they work is a combination of circular and linear polarization and polarizers. So on the front of these we have a circular polarizer, and on the back we have a linear polarizer. What that means is that if light is incident on the front, it gets circularly polarized, and it'll always make it through the linear polarizer. Well, if it's unpolarized or linearly polarized light. I'll demonstrate that it's not just a linear polarizer by looking at this linear polarizer through it. So if we do that and we rotate it, it never completely blocks out the light. In fact, it never really changes the intensity very much. But I said there was a circular polarizer and a linear polarizer. So if the light's moving this way, traveling this way, and encounters that linear polarizer first, it will be completely blocked. So if we flip the glasses around and now rotate them, we do see that complete blockage. So again, this way is linearly polarized to circular, which makes it through the linear, and it makes it through. This way, linearly polarized, blocked by linear polarizer, and then never sees the circular polarizer. So, how they do this is they send one circularly polarized, say left circularly polarized, that reflects off the screen, makes it through the circular polarizer, and makes it through the linear analyzer. On the other glasses, though, it's rotated the other way, and instead of, say, making it through horizontally and making it through this, is that right? Yeah, horizontally and making it through this polarizer back here, it becomes vertical and doesn't pass through that analyzer, that second polarizer. But that was for left polarized light. We can also have right circularly polarized light, which they use for the other image. That one makes it through this polarizer, but doesn't make it through this one. That's how we can get those two different images. Now, let's take a look and see also how these circular polarizers work. See if that's right. So, if we now start with unpolarized light, that first linear polarizer makes it linearly polarized. Then we have the front circular polarizer. So now we should have circularly polarized light out of the flashlight. And I said that it wouldn't make it through this one, and sure enough, it really doesn't. Well, there we go. We actually have to rotate a little bit. Okay, so what sort of cool experiments can we do with circular polarization? Well, one of my favorite actually involves a mirror, so this might be kind of tricky for me. What we're going to do is we're going to start with a flashlight on our circular polarizer. So you can see some of the lights making it through there, but now it's going to be circularly polarized. I'm going to bounce off the mirror, and from this angle we can still see it from the camera. Turn the camera up and look through the circular polarizer. Oh, it's extinguished most of the light. Well, what's going on there? Any ideas? Well, what's happening is that after it passes through the circular polarizer, it is, say, left circularly polarized. When it bounces off of the mirror surface, it becomes right circularly polarized on the way back up. And that right circularly polarizer then is rotated the other way, so it doesn't make it through the linear polarizer on the other side of this. Because remember, this is a circular polarizer and a linear polarizer. Well, thanks for watching. I hope you learned something about polarization today, and be on the lookout for examples of polarization in your life. See you later.